Good day, everyone. Thanks for joining us for our presentation. Our presentation is about green hydrogen from hydrokinetic energy, a clean and sustainable solution. This presentation will be done by me, Amara, and David. I will do the short introduction of our project, and before I go to the main project, I would like to shed some light on the hydrokinetic energy potential in Newfoundland and Labrador. Newfoundland and Labrador have a significant hydrokinetic energy potential due to their extensive coastline and numerous rivers. The region's estimated potential includes 544 megawatts of tidal current, presenting opportunity for tidal energy development in locations such as the Bay Island. In the Bay Island, harnessing hydrokinetic energy in this area could contribute to clean and sustainable energy generation. Then I would like to say to discuss about the global shift to sustainable energy. This is a global shift towards sustainable energy source is a response to the severe threat posed by the greenhouse gases and climate change. This shift aims to transition from fossil fuels to clean, low-carbon emitting energy sources such as renewable energy options. The momentum towards sustainability has been gaining significant traction in recent years, highlighting the importance of adopting green energy solutions to combat environmental challenges. After that, I would like to do the introduction of green hydrogen production using hybrid offshore renewable energy system. Green hydrogen production using a hybrid offshore renewable system involves utilizing renewable energy sources such as offshore wind and marine energy to power water electrolysis and produce hydrogen. This approach offers efficient and environmentally friendly energy generation, reducing carbon emission and providing adaptability and cost reduction. And after that, now I'd like to compare the of the electrolysis technologies. There are three electrolysis technologies. One is alkaline water electrolysis, the other is a polymer electrolyte membrane electrolysis, and the other one is the anion exchange membrane electrolysis, which we will be focusing in this project in the next semester. So the alkaline water electrolysis, the advantage of these are they are cost effective and have been widely used for hydrogen production, but the challenges are they are less efficient compared to other technologies and may have lower hydrogen purity. And the application are commonly used for large scale industrial hydrogen production. The proton exchange membrane electrolysis, the advantage of these electrolyses are highly efficient and have rapid response times, offer higher hydrogen purity, but the challenges are relatively more expensive than alkaline water electrolysis, and durability may be a concern in some applications. The anion exchange membrane electrolysis they shows promise in being more efficient than alkaline water electrolysis and having lower material cost than PAM. But the challenges are that these technologies are still under development and commercialization is in a progress. But the application of these electrolysis has potential for various hydrogen production application, particularly in renewable energy integration. From here, I would like to hand it over to my friend Amara.
Good day, my name is Amara, as introduced by my colleague Ali. So I will be taking us on the hydrokinetic and other renewable energy sources potential in Newfoundland. Our study location is Lewisbrook along Prince Phillips Drive, which has a river stream there close by and obviously has some hydrokinetic potential, which we are going to investigate. The location has an average annual rainfall that ranges between 1,200 to 14 millimeters. The geographical coordinates are seen in the slide. So we got our data from HOMA 2, and HOMA gets its data from NASA database. From the database, we see that this location records high wind speeds during December with 11.12 meter per second, and the lowest speed occurs in August with 7.62 meter per second, which is quite relatively high. We also see that from the database that we have the highest flow rate of water, and that happens in April with a value of 1.66 meter cube per second. The months of September, November, and December also record a high discharge flow rate as well. What this means is that during these months, we are expected to have the highest hydrokinetic energy contribution to our hybrid renewable energy system. Going forward, we are going to look at our energy component design. Basically, our component design, hybrid renewable energy system design consists of our hydrokinetic turbine, our wind turbine, our electrolyzer, our reformer, hydrogen tank, converter, and battery. We also believe that we are going to generate energy, which is also going to support the load, the grid, and this constitutes our electrical load. The reformer here is going to serve as a kind of buffer or as a backup to support the hydrogen load when there is inadequate renewable energy power supply. We are going to consider three case scenarios. A case A scenario, which consists of only the hydrokinetic turbine and the other components. A case B scenario that consists of a hydrokinetic turbine and wind turbine with the other components, and a case C scenario that comprises of only the wind turbine with our other components. Our specifications have been modeled and we have also sized our components and modeled them according to some equations, and this table gives a summary of what we are going to use for our design. Our hydrokinetic turbine having a capacity of 20 kilowatts, our wind turbine having a capacity of 30 kilowatts, and electrolyzer having a capacity our hydrokinetic turbine having a capacity of 20 kilowatts, our wind turbine having a capacity of 100 kilowatts, our electrolyzer having a capacity of 744 kilowatts. Worthy to note that these components have some associated costs. The capital cost here for the hydrokinetic turbine is about $20,000 per the 20 kilowatts. The wind turbine is about $1,300 per kilowatt, and our electrolyzer is about $200 per kilowatts. Going forward, for us to make the best decision from our HOMA Pro, we need to know some certain terms such as the net present cost, the levelized cost of energy, and the utilization of electrolyzer. The net present cost is basically the worth of all the costs incurred by the system over the system's lifespan minus the worth of the revenues earned during the project lifespan. That is what we refer to as a net present cost. Our levelized cost of energy is basically the average net present cost of the energy generated over its lifetime, and the utilization of energy is also the ratio of the total hydrogen produced under our given system variables to the maximum possible quantity of hydrogen that can be produced under ideal conditions. We need to know also that our tool for simulating our system design made up of certain specification is the HOMA tool, and the HOMA tool basically optimizes the system and gives us the best energy system in terms of sizing and cost. From the results, we see that out of these three cases and scenarios we came up with, Our case B scenario, which consists of both the hydrokinetic and wind turbine, happens to be the best and optimal case scenario. It comprises of going to comprise of 200 kilowatt wind turbine with 520 kilowatt hydrokinetic turbine and one string of battery. We see from our results that although our case C scenario, which consists of only the wind turbine, has the lowest net presence cost of $3.5 million, but case B, which is our optimal design, also has a relatively low cost of about $3.64 million and a levelized cost of energy of $68.49 per kilowatt hour. Going forward to further cement that case B is the best choice, we see that case B recorded the highest electrolyzer utilization of 81%, producing about 374 kilogram of hydrogen. Case A comes next with 50% electrolyzer utilization with 234 kilogram of hydrogen. With this, I end my own section and I hand over to David to give us his insights and analysis on the electrolyzer itself. Thank you.
So, as mentioned by my partner, we'll be comparing the alkaline water electrolysis method to the proton exchange membrane method under similar conditions. The reason we are comparing them under similar conditions is so we can get as fair a comparison as possible between both methods. The chosen state conditions are 70 degrees Celsius and another 30 bars of pressure. We chose these particular conditions because we learned that under this 70 degrees Celsius and 30 bar, both techniques can function and produce hydrogen gas. The reactant conversion, that is the amount of water that will be converted to evolve gases within the electrolyzer, was taken at 65% for both methods. And the alkaline, it's important to note that the alkaline water electrolysis method would require a mixture of some form of alkaline with the feed water, with the pure feed water, in order to generate the process feed. Now, this is not the case for the proton exchange membrane method, as an alkaline medium is not necessary or needed at all in that case. Now, both techniques had seawater coming in at a mass flow rate of 1,658 kilograms per hour under atmospheric conditions. Now, both techniques also had to undergo a desalination process where, where salts or dissolved salts were separated from the pure water or pure purified water stream. Now, for the alkaline water electrolysis method, this purified water was then added or combined with alkaline coming in, as well as recycled um, unconverted water from further down the process, which came back to be reused as process feed. For the PEM, it didn't have to undergo this alkaline method, but it was also mixed with recycled unconverted water, which came from down the stream. The flow process diagram will explain this point more clearly. Now here we have the process flow diagram for the alkaline water electrolysis method, which was designed using Aspen HYSYS. Here, the process starts here with seawater being fed in at a mass flow rate of approximately 1,658 kilograms per hour. The impure seawater is then sent to a desalination unit first in order to purify it, and salts are removed using the reverse osmosis method. The purified water then goes on to be mixed with two further streams. Firstly, we have the alkaline stream. This alkaline stream consists of 25% potassium hydroxide solution, and the second stream is a recycled stream which consists of unconverted water from the electrolyzer, which I will get to shortly. After the mixer, the combined stream, the new mixture, is then pumped and heated to um, the earlier stated conditions of 70 degrees Celsius and 3 bar. This is known as the process feed. Now, this process feed goes into the electrolyzer to be separated into gases and into the gases we are looking for. Now, this electrolyzer, as stated earlier, undergoes a 65% reactant conversion rate, which is which simply means that 65% of the water which it is which is passing through it is converted into the processed gases, which are the products we need. The processed gases are vaporized, while the unconverted liquid water flows but flows through the bottom as liquid in the liquid phase. Now, I'll address the gases first. The gases are then further sent to a separator, and after which the less dense hydrogen gas, our primary product, is separated from the denser hydrogen gas. Although now both gases from this point on are then compressed for further processing, each through its own stream. Now back to the electrolyzer. The water that was on the unconverted water that comes out from the electrolyzer is then sent back through a recycled stream to the aforementioned mixer. This is where the third stream comes from. Now here we have the process diagram for the proton exchange membrane technique. The process is basically the same for both systems. However, the main difference here is the fact that we would notice, if you look here, we would notice that there is no alkaline stream. This affects the entire process going downstream, and these results will be discussed later. But it is important to keep in mind for our understanding that the process is basically the same through this flow diagram. Now we have come to the results of our Aspen simulation, and here we deemed that the proton exchange membrane technique outperformed the alkaline water electrolysis technique. It produced more hydrogen under the same conditions, it consumed less energy under the same conditions, and it produced marginally less greenhouse gases as well under the same or rather similar conditions. And finally, our, our interest in this research is to develop a cost-effective means of generating hydrogen using modular means, if possible, to produce hydrogen, and we want to use hydrokinetic means to achieve this goal. Now, unfortunately, we cannot deploy PEM, that's proton exchange membrane technology here, because for several reasons and disadvantages it has. One of them is that it is energy intensive, and it still requires reverse osmosis method to purify the saltwater feed which we have chosen. Secondly, PEM is inherently expensive. Thirdly, that is why we have chosen to use the anion to, or rather to develop the anion exchange membrane technology and incorporate it into our work. That in future, our future work is geared towards that direction. We're going to rerun or something, think of something similar or conduct something similar using the anion exchange membrane, which is still in its infancy. So we may need to go into the laboratory or conduct further research in order to get some important data, such as the conversion rate of AEM, that's anion exchange membrane reactors. Another new technology or cheaper technology that we are considering for the energy generation aspect is the triboelectric nano generator. Those could be used in energy generating devices, and they are showing a lot of potential. Thank you for your time.